The appearance of a bell-like character in the binomial distribution suggests that we take a closer look at the popular bell curve. The bell curve in the popular language is more formally known as the normal density. The terminology is due to Francis Galton and Carl Pearson, who coined it in the early part of the 20th century because of its apparent prevalence in all kinds of sundry applications. It was the normal curve. It is also in some quarters called the Gaussian density. The first person to make extensive use of this was Carl Friedrich Gauss in the early part of the 19th century. So, we're all familiar with the bell curve. Well, what is it formally and mathematically? Well, mathematically, using Gauss's notation, we call it a function, little phi of x. Phi of x has got this particular form. It's not completely an elementary function, is it? But it's not a difficult function. What does it behave like? What does it look like? Well, the graph is something we're all very familiar with. Casual acquaintance in the popular literature has made us very familiar with this curve. It's got a bell-like character. It's completely formally characterized by the mathematical equation above it. Now, this is the standard bell curve, the normal density. The listener who has braved the dangerous bend Tableau 6 Part 2 will have seen this make an incidental appearance as an example of a density. Now, we're going to put it to use. Now, our observation that the normal density, the bell curve, could fit the binomial mass function suggests that probabilities might be attainable by computing areas. In other words, we've taken a combinatorial problem and reduced it to a geometric problem, one of computing areas. It will be useful to get some nomenclature here, some terminology under our belts up front before we go into the details. So accordingly, pick any point t on the x-axis. Our objective is to characterize the area under the bell curve to the left of t. In other words, the area all the way in principle from minus infinity up till t. Now, of course, today we can compute this easily and simply on any modern computer, or one could even just type it into the internet and get a quick numerical free estimate. So this is easy to do. Now, consider what happens as we move t. If t moves to the left towards minus infinity, then the area decreases smoothly. And in the limit near minus infinity, the area is exactly 0. So the area increases from 0 at minus infinity all the way through t, and as it goes past this point, as t increases all the way to plus infinity, the area keeps increasing. We've got a positive function, and therefore the area will increase as the endpoint moves to the right. And then what happens as the endpoint t goes to plus infinity? Well, at that point, we get the entire area under the curve. One of the reasons for defining the curve in exactly this fashion with a normalizing factor 1 over the square root of 2 pi is that the area has been normalized to unit. And therefore, if we plot as a function of t what happened to the area from t all the way to the left, we find that the area increases smoothly, starting at 0 at minus infinity, and then you have a smooth S-shaped curve. And the curve saturates with an area 1 at plus infinity. In other words, we've described a function of a real variable t. This particular function has a name. It's called the normal distribution function. And of course, it's got a symbol which characterizes it. We've used the lowercase Greek letter phi to characterize the normal curve, the bell curve, the density. We use the uppercase Greek letter phi to characterize the distribution function associated with it. And formally, of course, an area in the language of calculus is an integral. So if you've had any calculus, you could write down an expression, at least a formal expression, for the distribution function, big phi of t, as the integral from minus infinity to t of little phi of x. What does this mean? Well, this just means, and if you're not familiar with integration, we just take it to mean the area under the curve from minus infinity up to a point t. As we allow t to vary, we get a smooth and increasing function, the distribution function of the normal. Now, this is a starting point. The idea is that the big phi, the distribution function, captures an area, and we should be able to put that to use in capturing probabilities. Let us turn now to the properly scaled and centered binomial variables, Sn star given by Sn minus n over 2, properly scaled to square root of n over 2, and we saw that Sn star has got a particular mass function. Let us see what happens now if we attempt to fit a properly normalized bell curve through these points. And if we do that, we find really a quite remarkably good fit. A closer examination shows that the fit is least effective when n is small. But as n becomes larger and larger and larger and larger, the fit gets better and better and better and better, quite alarmingly so. Now, how do we compute probabilities from a discrete setting? Well, we simply sum up the mass function, the atomic probabilities. For example, if we are interested in the question, what is the chance that Sn star takes values in a given interval? We just sum up the masses inside that interval. If we ask, what's the probability that Sn star takes values no larger than some given t, then we just sum up all the masses of Sn star up till that point t. Of course, if t is considered to be a variable, then we get a function of t. This is called the distribution function of your scaled variable Sn star. How does the distribution function look like? Well, let's think about it first. A generic Sn star has got mass functions which look like this bell curve. You've got little things which go up and down like this and then decrease smoothly. Now, if you want to add up the masses up to a given t, then you're going to start out near infinity at 0, and then the first time you hit a mass, the value jumps up by that mass amount, and then stays flat till the next mass. It jumps up by that mass amount, stays flat, jumps up. Of course, the sizes of the steps are varying. They depend upon the masses of the atoms that you encounter. But we ineluctably have a step character for this function Fn star. Of course, we're going to try to approximate this step function by simply looking at the area under the bell curve. But that is a smoothly increasing function. How do they compare? Well, let's take a look. When n equal to 10, you can see the step function for Sn star, the distribution function, and cutting through it, the smooth variation of the distribution function. And already you say that the distribution function of the normal is already very close everywhere to the distribution function, the probabilities for the standardized binomial. As n increases, the fit gets better and better and better. And at n equal to 100, the fit is quite remarkably good. The pictorial evidence is very, very strong here, right? This suggests that probabilities for binomials viewed in the proper scale may be well approximated by appropriate areas under a bell curve. This visual evidence is compelling and takes us to this powerful discovery from 4 centuries ago.